Scientists thought black holes were the ultimate monsters of the universe until Phoenix A appeared, and even that definition began to break. Phoenix A may not simply be swallowing matter. It may be revealing a physical limit that current models still cannot fully explain. Before we go further, like and subscribe, because this object could change the way we understand the most powerful objects in the universe. Now, let's begin. You already know the name, Sagittarius A star, the supermassive black hole sitting at the dead center of our own Milky Way galaxy, 4 million times the mass of our Sun. Photographed directly for the first time in 2022 by the Event Horizon Telescope. That image, a blurry but glowing ring of fire suspended in darkness, broke the internet. Scientists cried in press conferences. It was, by every reasonable measure, one of the most extraordinary things our species had ever seen. Then someone pointed a telescope at the Phoenix cluster, and the word terrifying needed to be completely rebuilt from scratch. Phoenix A weighs 100 billion times the mass of our Sun. Not 100 million, not 1 billion, 100 billion. That is 25,000 times more massive than Sagittarius A star. The black hole we just finished calling the most frightening thing we'd ever documented. If Sagittarius A star is a monster, Phoenix A is the thing that monsters tell stories about to frighten their children. And it sits 5.7 billion light-years away from us. Let that distance breathe for a moment. 5.7 billion light-years means the light we're receiving from Phoenix A right now. The data our telescopes are capturing, the images our scientists are analyzing, left its source before our Sun existed, before Earth existed, before the rock that would eventually become our planet had even begun to coalesce from a cloud of stellar debris. When that light began its journey toward us, there was no solar system here, no Milky Way arm where we currently reside, nothing that would eventually become you, or anyone you've ever known, or any civilization that ever rose and fell on this particular rock. We are not just looking at something distant. We are looking at something ancient in a way that collapses every human concept of time into irrelevance. But here is where it stops being merely large and starts being something else entirely. The event horizon of Phoenix A spans approximately 370 billion miles across. 370 billion. Light traveling at 671 million miles per hour. The absolute speed limit of the physical universe needs 3 full weeks to cross from one edge to the other. This is not a point in space. This is not a hole in any sense the word originally implied. This is a territory, a region, a domain with a scale that makes the word boundary feel almost comically inadequate. If you placed Phoenix A where our Sun currently sits, its event horizon would not just swallow Mercury, Venus, Earth, and Mars. It would extend past Jupiter, past Saturn, past Uranus and Neptune, past Pluto, and keep going, stretching out into the Kuiper Belt, where the frozen remnants of our solar system's formation drift in eternal cold silence. Everything, every planet, every moon, every asteroid we've named and argued over all of it would sit comfortably inside the event horizon of a single object. We need a comparison that actually lands. If Sagittarius A star were a basketball placed at center court inside Madison Square Garden, Phoenix A would not be a bigger basketball. It would not be the entire arena. Phoenix A would be the entire city of New York, every borough, every block, every building, every subway tunnel running beneath it, and then some. Same category of object. The textbooks say, profoundly, fundamentally different in every way that matters. Then there is the silence that came before. For hundreds of millions of years, a span of time so long that our entire recorded human history fits inside it, the way a single sentence fits inside a novel. Phoenix A sat in near darkness, quiet, not consuming, not radiating with the ferocity it's capable of, not announcing itself to the universe in the way active black holes do, just existing, waiting, if we want to be poetic about it, and the universe, for hundreds of millions of years, obliged. Then something changed. Phoenix A woke up, and it began eating again, consuming infalling matter at a rate that produces some of the most extreme energy output ever recorded in the known universe. The central galaxy of the Phoenix cluster lit up. X-ray observatories detected the signature of a system going from dormant to ferociously active. The data was unambiguous after its long silence. The giant had stirred. What woke it? That question alone will lead you somewhere far more unsettling than the size of the thing itself. The answer involves the structure of the cluster surrounding it, the behavior of cooling gas on scales of millions of light years, and a failure of a cosmic mechanism we thought was essentially universal. We'll get there. The short version, what woke Phoenix A, was a breakdown, and the consequences of that breakdown are still unfolding. Something that sleeps for 500 million years and wakes up healthy. What exactly is it? And when something that large wakes up hungry, what does hungry even mean at that scale? We lose sleep over deadlines, over bad news, over the low hum of anxiety that modern life generates in industrial quantities. Phoenix A slept for 500 million years and woke up in perfect working order. Arguably, the universe's best wellness strategy is simply do nothing for 500 million years. Most of us don't have that kind of patience. Phoenix A has nothing but the size and the awakening. Those are just the surface. The environment Phoenix A actually lives in, the galaxy cluster wrapped around it, like the most extreme neighborhood in the observable universe, is the thing that keeps astronomers genuinely awake at night. Galaxy clusters are the largest gravitationally bound structures in the observable universe. Full stop. Not galaxies clusters. A single galaxy cluster can contain anywhere from a few hundred to several thousand individual galaxies, all locked together by gravity into one massive system. But the galaxies themselves are almost a footnote. The real substance of a cluster, the majority of its ordinary matter is not stars. It is gas, superheated plasma filling the vast spaces between galaxies, glowing at temperatures of tens of millions of degrees, invisible to the human eye but blazing in X-ray light. Astronomers call this the intracluster medium. It is, by volume, the dominant feature of every cluster ever studied. These systems are ancient, enormous, and by the standards of the universe, relatively well understood. We have cataloged hundreds of them. We have measured their temperatures, their masses, their X-ray luminosities, their rates of star formation. We have built models that predict how they evolve, how their central black holes interact with the surrounding gas, how energy flows through the system over billions of years. The science is mature. The framework is solid. The Phoenix cluster walked into that framework and broke every single instrument at once. Not one record, not two. The Phoenix cluster holds multiple simultaneous records across completely independent categories. The highest X-ray luminosity ever measured in a galaxy cluster, the strongest cooling flow ever observed, and the highest rate of star formation ever recorded in a cluster environment. 3 separate phenomena, 3 separate measurement techniques, 3 separate research teams, and every single one came back with the same answer off the charts. When a system breaks one record, you investigate. When it breaks all of them at the same time, you start questioning whether your charts were ever drawn correctly to begin with. And here is the detail that nobody talks about enough. The Phoenix cluster was not discovered by Hubble, not by the James Webb Space Telescope, not by Chandra, not by any of the instruments specifically designed and launched to find extreme objects in the deep universe. It was found in 2010 by the South Pole Telescope, a facility built not to photograph galaxies, not to detect X-rays, but to map the cosmic microwave background, the faint afterglow of the Big Bang itself, using millimeter wavelength radio waves. The South Pole Telescope was essentially doing something else entirely when it stumbled across one of the most extreme environments in the known universe. That alone should tell you something about how unusual this object is. The universe hid it in plain sight, and we found it almost by accident. Once astronomers knew where to look, the follow-up data came fast, and it came brutal. X-ray observations from the Chandra X-ray Observatory confirmed what the initial detection had suggested. Gas is falling toward the center of the Phoenix cluster at a rate hundreds of times greater than what is seen in a typical cluster. Hundreds of times, not 10% more, not double. Hundreds of times the normal rate of infall, sustained, continuous, with no sign of the feedback mechanism that should, by every model we have, be slowing it down. This is what astronomers call a cooling flow. Hot gas in the intracluster medium radiates energy, loses heat, becomes denser, and begins to sink toward the gravitational center of the cluster. In most clusters, this process is self-limiting. The central black hole responds, pumps energy back into the gas, reheats it, and the system finds equilibrium, a thermostat, a feedback loop that has been operating reliably across thousands of clusters for billions of years. In the Phoenix cluster, that thermostat is not working. The gas is cooling faster than any compensating mechanism can respond. And the result is the most powerful cooling flow ever recorded, a cosmic drain with no shutoff valve. Picture a bathtub drain. Simple enough. Now scale that bathtub to something spanning several 100 million light years across. Fill it with plasma at 50 million degrees and remove any possibility of the drain ever slowing or stopping. Everything in that system, every cubic light year of superheated gas is being pulled, inexorably, toward the center. And at the bottom of that drain, waiting with the patience of something that has existed for longer than our sun, is Phoenix A, mouth open, the strongest cooling flow ever observed, feeding directly into the most massive black hole we have ever found. The drain and the void are perfectly matched, and the system has been running, unchecked, for longer than the Earth has existed. Now consider what this looks like in raw energy terms. The Phoenix cluster radiates X-rays at a luminosity that places it at the absolute top of every ranking ever compiled for structures of its kind. If human eyes could detect X-ray wavelengths, if we had evolved to see the universe the way Chandra sees it, the Phoenix cluster would appear on our night sky thousands of times brighter than the entire Milky Way. Not a faint smudge requiring a telescope. A blazing, overwhelming source of light that would dominate the sky with a ferocity our galaxy cannot come close to matching. This is not a quiet corner of the universe. This is not a stable, mature system coasting through cosmic time. This is a furnace, an engine running at maximum output with no governor on the throttle. We are staring directly into it from a distance of 5.7 billion light years. And that distance is the only reason the word safe applies to our current situation. You might be thinking, fine, bigger cluster, stronger signals, more extreme numbers, but fundamentally the same kind of object. Just a louder version of things we already know? That is exactly what the scientific community assumed before the data from Phoenix started coming in. That assumption is exactly what the data destroyed. The Phoenix cluster is not a louder version of a familiar system. It is a system operating in a regime that existing models were not built to describe, and the object at its center is the reason those models keep failing. Someone named this cluster Phoenix after the mythological bird that burns to ash and resurrects itself, cycling endlessly between destruction and renewal. Nobody knew when that name was assigned how precisely it would describe what is actually happening at the cluster's core, a black hole that slept for hundreds of millions of years, a system that erupted back into activity with enough force to shatter every benchmark we had, rising from its own dormancy like something out of mythology, except the mythology turned out to be real, and the numbers attached to it turned out to be far stranger than any story we invented. To understand why Phoenix A is not just larger, but genuinely something else entirely, you need to know how science classified black holes in the first place and why that classification system just got torn apart. For most of modern astrophysics, black holes came in two flavors. That was it. 2. The universe, for all its complexity, seemed to have settled on a remarkably tidy arrangement when it came to these objects, and for decades, the tidiness held. The first flavor, stellar mass black holes. These form when a massive star exhausts its nuclear fuel, collapses under its own gravity, and detonates in a supernova. What remains is a black hole typically ranging from a few times to a few dozen times the mass of our Sun. Violent in origin, small by cosmic standards, scattered throughout galaxies like punctuation marks at the ends of stellar lives. We have found hundreds of them. We understand the mechanism that creates them reasonably well. They are extreme, yes, but extreme in a way that fits inside existing physics without causing too much trouble. The second flavor, supermassive black holes, millions to billions of solar masses, sitting at the centers of galaxies. Their origins murkier and their scales incomparably larger than their stellar cousins. Sagittarius A star at 4 million solar masses. The black hole at the center of M87, the first ever directly imaged. In 2019, at 6.5 billion solar masses. These are the anchors of galaxies, the gravitational engines around which hundreds of billions of stars organize their orbits over billions of years. Between these two groups sat a conspicuous gap. Intermediate mass black holes objects in the range of hundreds to hundreds of thousands of solar masses were theorized, but frustratingly elusive. For years, finding and confirming them was considered one of the pressing open questions in astrophysics. The assumption was clear: the frontier lay in the middle. Fill the gap between stellar and supermassive, and the picture would be complete. Two anchors, one missing bridge. Solve the bridge. Close the book. Nobody was looking above the upper anchor. Nobody thought there was anything above it worth looking for. Then the data from the early 2000s started arriving, and the book turned out to have chapters nobody had written. NGC 1277, a compact galaxy sitting inside the Perseus cluster, approximately 250 million light-years away. When astronomers measured the black hole at its center, the number that came back was staggering, somewhere in the range of 17 billion solar masses. 17 billion. At the time, this represented a significant fraction of the entire stellar mass of the host galaxy, a black hole so disproportionately large relative to its surroundings that it forced immediate questions about how such a thing could even form. The galaxy looked almost like an afterthought wrapped around a black hole, rather than a black hole living inside a galaxy. Then came TON 618, a quasar, an actively feeding black hole blazing with the energy of infalling matter, with a central mass of 66 billion solar masses. 66 billion. A number so far beyond the upper end of what supermassive had implied that the category itself became awkward. Calling TON 618 a supermassive black hole felt like calling the Pacific Ocean a large puddle. Technically defensible, practically useless. Astronomers needed new language. The term that emerged, ultramassive black holes, or UMBHs, defined as black holes exceeding 10 billion solar masses. A new category, carved out above the existing maximum, because the existing maximum had been quietly exceeded by objects that the old framework simply had no room for. The gap that needed filling, it turned out, was not in the middle. It was above everything astronomers had previously thought represented the ceiling. The ceiling, as it happens, was not a ceiling at all. Phoenix A sits at 100 billion solar masses. It does not merely qualify for the ultramassive category, it pushes against the theoretical boundaries of what that category can contain without the underlying physics beginning to break down. Theoretical astrophysics places constraints on how massive a black hole can become through standard accretion, the process of consuming infalling matter. There are limits rooted in the Eddington limit, in spin dynamics, in the relationship between a black hole's mass and the maximum rate at which it can sustainably grow. These are not arbitrary numbers. They emerge from the same equations that describe the behavior of light, matter, and gravity across the universe. Phoenix A is approaching a regime where those equations start producing answers that do not comfortably resolve. Not wrong answers, necessarily, but answers that require assumptions our current models may not be equipped to make. The spin limit of a maximally rotating black hole, described by the Kerr metric in general relativity, places constraints on energy extraction and event horizon geometry that become increasingly difficult to interpret at these mass scales. The accretion limit, the maximum rate at which a black hole can consume matter before radiation pressure pushes material away, has implications for growth timelines that Phoenix A appears to strain against. The models do not fail cleanly. They begin to give results that physicists look at with a particular expression. The expression of someone who suspects the map they are holding does not accurately represent the territory. This is not a discovery of a larger version of a known thing. This is evidence that the universe can produce objects for which our current physical vocabulary is genuinely insufficient. The analogy is exact. Imagine spending your career cataloging buildings. You have a rigorous system by height, by volume, by structural type. You are confident the system is complete. Then someone takes you to a location and points at something on the horizon and asks you to classify it. And what you are looking at is the size of a small country. Your cataloging system does not fail because it is wrong. It fails because it was never designed to handle something that exists in a fundamentally different scale of existence. And here is where the question shifts from how large is it to something far more unsettling. The real question is not what Phoenix A weighs. The real question is why the universe permits it. Is there a theoretical upper mass limit for a black hole? The honest answer from the astrophysics community right now, nobody is certain. The equations of general relativity, in principle, place no hard upper bound on black hole mass. There is no line in the mathematics that says, beyond this point, the object cannot exist. But there are regions of the parameter space where our understanding of the interior of what space-time looks like inside an event horizon of this scale becomes genuinely uncharted. Some theoretical physicists have suggested that beyond certain mass thresholds, the interior structure of a black hole may operate according to rules that differ meaningfully from what we extrapolate from smaller objects. The singularity at the center, the behavior of quantum fields near the event horizon, the thermodynamic properties of the system. All of these become progressively harder to describe with confidence as mass increases beyond anything we have ever been able to directly test. Phoenix A is not just large. It is large enough to sit in a region of physics where the theories we trust have never been verified against observation. If the classification system collapses, if supermassive meant nothing once we found ultramassive, and ultramassive strains at its seams the moment Phoenix A enters the room, then what exactly are we classifying? What does the label black hole actually mean when the object wearing that label operates in a physical regime our equations cannot fully describe? Astronomers spent decades building a clean, coherent taxonomy. Two groups, one gap, a research agenda aimed at filling the middle. The universe responded by producing Phoenix A, as though the cosmos had glanced at the organizational system, found it charming, and then proceeded to do whatever it wanted regardless. Cute system. Anyway, but a new category is just a name. What truly breaks your understanding is when you stop and look directly at the actual dimensions of this thing and realize that ordinary physical language no longer has the tools to describe what is happening there. If you have spent any time watching science content online, you have almost certainly encountered TUN 618 as the final word on black hole scale. It appears in countless videos, articles, and comparison graphics, the ultimate reference point, the thing at the top of every largest known black holes list, the object that reliably produces the reaction. Okay, I cannot comprehend this. We are done here. 66 billion solar masses. The number that ends the conversation? TON 618 earned that reputation. It is genuinely extraordinary, a quasar of almost incomprehensible luminosity. Its central black hole outweighing the stellar populations of many entire galaxies. When science communicators reach for the most extreme example of what the universe can produce, TON 618 is the natural endpoint, the ceiling, the thing beyond which the implicit argument goes, there is nothing left to find. Phoenix A outweighs it by more than 50%. 100 billion solar masses against 66 billion. The object that was supposed to be the final answer is not the final answer. It is not even close to the final answer. And the more important distinction, the one that changes the entire meaning of the comparison, is not the mass difference. It is the context in which each object exists. TON 618 is observed at a redshift of 2.219. In practical terms, that means the light we receive from it left its source approximately 10.4 billion years ago. We are not seeing TON 618 as it exists now. We are seeing it as it existed when the universe was roughly 3.4 billion years old, a young, chaotic cosmos packed with gas, actively forming galaxies at a furious rate, and producing quasars with an intensity that the modern universe simply does not replicate. TON 618 belongs to that early era. It is a relic of a time when the conditions for creating such objects were abundant, and the universe had not yet settled into the relatively calmer structure we inhabit today. Phoenix A sits at a redshift of approximately 0.596. That translates to a look-back time of roughly 5.7 billion years, meaning we are observing it at a period when the universe was already more than 8 billion years old. By cosmic standards, this is not the ancient, turbulent early universe. This is the universe in a relatively mature phase, long past the peak of quasar activity, long past the era when extreme objects of this kind were supposed to be common. The conditions that produced TON 618 were fading billions of years before the light from Phoenix A began its journey toward us. This is the distinction that matters. TUN 618 is extreme, but it is extreme in a context where extreme things were expected. The early universe was wild. Everybody knew that. Quasars blazing at impossible luminosities, black holes growing at staggering rates, galaxies forming and colliding with a frequency that the modern universe has largely left behind. The early universe being dangerous and excessive was not a surprise. It was consistent with the theory. Phoenix A being this large, this active, this energetically extreme in the relatively modern universe that is the surprise. Science had a quiet reassurance built into its understanding of cosmic evolution. The worst of it is behind us. The most extreme objects, the most violent environments, the most incomprehensible concentrations of mass, those belong to the early chapters. The universe grows up. It settles down. By the time you reach a look-back time of 5.7 billion years, the expectation was a cosmos that had largely moved past the era of monsters. Phoenix A did not receive that memo. Its activity, the furious infall of gas, the starburst, running at hundreds of times the rate of a normal galaxy, the X-ray luminosity that breaks every cluster record, is happening in an epoch when this level of extremity was supposed to be history. Not ancient history, recent history. By cosmic standards, the universe had been calm enough, long enough, that finding something like Phoenix A still operating at full capacity in this era forces a genuine reconsideration of how well we understand the timeline of cosmic evolution. And Phoenix A is not alone in issuing this challenge. The confirmed and candidate ultramassive black holes currently known number roughly a dozen, but that number grows with each year as new instruments come online and survey strategies improve. More significantly, the James Webb Space Telescope has been systematically finding massive black holes at earlier and earlier epochs in cosmic history. Objects appearing within just a few hundred million years of the Big Bang that are far larger than our models predicted they could be at those ages. The pattern is consistent across multiple independent lines of evidence. The universe appears to have been producing extreme black holes faster, earlier, and in greater numbers than the standard framework anticipated. Phoenix A is the most visible data point in a broader problem. It is the largest, the most active, the hardest to ignore. But the discomfort it creates is not unique to it. It is the sharpest expression of attention that is building across the entire field of black hole cosmology. You might be sitting with the thought, fine, it is large, the timeline is surprising, but fundamentally, the physics is the same. Gravity is gravity. Accretion is accretion. We understand how these systems work. We just need to adjust some parameters. That response is understandable. It is also what physicists said before each of the last several major revisions to the standard model of cosmology. Look directly at the actual scale of Phoenix A, 370 billion miles of event horizon, 100 billion solar masses, active in an era of the universe when this was not supposed to be possible, and then try to hold the position that nothing fundamental needs revisiting. Science coined ultramassive when the numbers demanded new language. The term sounds authoritative. It sounds like the kind of word that closes a chapter rather than opening one. Then the universe kept finding things that made even ultramassive feel provisional, and the scientists who coined it had to sit down, open their laptops, and start considering whether they would need to do this again. The honest answer is probably yes. Numbers and categories are human language labels we press onto things we do not yet fully understand. To actually feel what Phoenix A is, you need to stand at the edge of its event horizon, and that is where physics starts doing things that are completely counterintuitive. Every explanation of a black hole eventually arrives at the same two words: event horizon, the boundary, the point of no return, the line drawn in space-time beyond which the escape velocity exceeds the speed of light, meaning nothing, not matter, not radiation, not information of any kind, can ever cross back out. It is one of the cleanest, most dramatic concepts in all of physics, and it translates remarkably well into plain language. A line you cannot uncross, a door that only opens one way. For Sagittarius A star, that boundary has a diameter of roughly 15 million miles, approximately 17 times the diameter of our Sun, enormous by any human measure. But in the context of a galaxy spanning 100,000 light-years, it is essentially a geometric point, a location, a precise address in space where the rules change and everything that crosses it is lost. The concept fits neatly inside the word boundary. You can picture it, a threshold, a line. Now take that picture and set it on fire. The event horizon of Phoenix A has a diameter of approximately 370 billion miles. 370 billion. The distance from our Sun to Pluto, a journey that took the New Horizons spacecraft nearly a decade to complete traveling at speeds no human vehicle had previously achieved is roughly 3.6 billion miles. The event horizon of Phoenix A is more than 100 times that distance across, 100 times the width of our entire solar system, edge to edge, just to span the boundary of a single object. Light covers roughly 671 million miles every hour without pause, without friction, without anything slowing it down the absolute speed limit of the physical universe. To cross the event horizon of Phoenix A from one side to the other, light needs 3 full weeks, 21 days of uninterrupted travel at the maximum velocity the laws of physics permit, just to traverse what we are still technically calling a boundary. This is no longer a boundary. A boundary implies a line something you cross in a moment, a threshold with negligible width. What Phoenix A possesses is a territory, a domain, a region of space with the geographic scale of a small stellar system, inside which the rules of physics have already changed and from which no exit exists. The word horizon, borrowed from the human experience of standing on Earth and seeing the edge of the visible world, collapses under the weight of what it is being asked to describe. Place Phoenix A where our sun currently sits. Its event horizon does not stop at Mercury, Venus, Earth, or Mars. It does not stop at the asteroid belt. It does not stop at Jupiter, with its 400-year storms and its ocean of liquid metallic hydrogen. It does not stop at Saturn, at Uranus, at Neptune. It reaches past all of them, past every planet in our solar system, past every moon we have named and argued over, past the dwarf planets orbiting in the cold dark beyond Neptune, and extends deep into the Kuiper Belt, where the frozen debris of our solar system's formation drifts in silence 4 billion miles from the sun. Everything, the entire solar system, 4.6 billion years of gravitational assembly, 8 planets, more than 200 known moons, billions of asteroids and comets, and chunks of primordial rock. Every single piece of it would sit inside the event horizon of Phoenix A. Not near it, not approaching it, inside it. Already past the point of no return, already in a region of space-time from which no signal, no light, no information could ever escape to tell the outside universe what was happening within. Our entire solar system would be a grain of dust inside a room the size of a continent. And now, the layer that most people never reach, because most explanations stop at the scale comparison and call it done. What is actually happening to space-time at the edge of this thing? Gravitational time dilation. The slowing of time in the presence of strong gravitational fields is a confirmed, measured phenomenon. GPS satellites require relativistic corrections because time passes slightly faster for them in orbit than it does on Earth's surface. Near a stellar mass black hole, this effect becomes extreme. Time near the event horizon slows to a near standstill. Relative to a distant observer, the gradient so steep that even small distances produce enormous differences in the rate at which time flows. Phoenix A does something stranger. Its gravitational influence is spread across a region of space 370 billion miles across. The gradient, the rate at which gravity changes from one point to another, is spread out over an almost incomprehensible volume. Time dilation at the edge of Phoenix A's event horizon is significant, but the change happens gradually, across vast distances, rather than spiking catastrophically over short ones. The curvature of space-time is profound, but it is distributed, stretched thin across a territory rather than concentrated at a razor's edge. The result is a paradox that requires a moment to absorb. The largest, most gravitationally dominant object we have ever identified produces, at its own boundary, a space-time environment that is in some ways less immediately violent than what you would encounter near a black hole 1/billionth its mass. The curvature is real, the dilation is real, but the gradient, The thing that tears, that shreds, that produces the physics of destruction is gentler at the horizon of Phoenix A than at the horizon of objects that are, by comparison, almost trivially small. This is not a comfort, it is a setup. If everything you know, every planet, every moon, every place any human probe has ever traveled, fits inside this boundary as a speck of dust in a continent-sized room, where exactly does that leave you in the picture? Not metaphorically, literally. You are made of atoms forged in stars, living on a rock orbiting one of 400 billion stars in one of hundreds of billions of galaxies. And somewhere out there, a single object exists whose boundary is large enough to contain your entire cosmic neighborhood with room to spare, operating under rules of space-time that make the familiar geometry of your existence feel like a local approximation of something far stranger. We spent a decade arguing whether Pluto qualifies as a planet. Committees were formed, papers were written. Public opinion was divided with an intensity usually reserved for matters of genuine consequence. Phoenix A could swallow Pluto, the entire debate, every astronomer who participated in it, the building where the vote was held, and the solar system those astronomers live in simultaneously, without noticing, for breakfast. Technically speaking. But here's the part that makes physicists look at each other and then look back at the data at the largest and most terrifying object we have ever found. The pull at its boundary is gentle to the point of being nearly imperceptible, and that is 100 times more frightening. Spaghettification. It is one of those rare scientific terms that does exactly what it says. When an object falls toward a black hole, the gravitational pull on the near side, the side closer to the singularity, is stronger than the pull on the far side. This difference in force across the length of a body is called a tidal force, and near a sufficiently small, sufficiently dense black hole, it becomes catastrophic. The body stretches, elongates. The near end accelerates faster than the far end, and the object, whether a star, a spacecraft, or an astronaut, is pulled into an increasingly thin strand of matter, like taffy being stretched by a machine that has no off switch. For stellar mass black holes, this process begins well outside the event horizon. A human body approaching one of these objects would be torn apart into a stream of particles long before crossing the point of no return, destroyed in open space, in full view of any observer watching from a safe distance, with no ambiguity about what was happening and why. The violence is external, immediate, and unmistakable. The physics announces itself. Phoenix A does none of that. At the edge of Phoenix A's event horizon, 370 billion miles from the center, at the precise boundary beyond which no return is physically possible, the tidal force acting on a human body is weaker than the tidal force our own moon exerts on Earth's oceans, weaker than the force that raises and lowers the tides twice a day on a planet you consider unremarkable. The same phenomenon that moves billions of tons of seawater across coastlines worldwide is more mechanically violent at the surface level than what Phoenix A produces at its own point of no return. The reason is geometry. Tidal force is not simply a function of gravitational strength. It is a function of the gradient of gravitational strength. How rapidly does the pull change from one side of an object to the other? For a small, dense black hole, the event horizon is close to the singularity, and the gravitational field changes ferociously over short distances, a steep gradient, a sharp drop, an immediate and overwhelming difference between the near side and the far side of anything that ventures close. For Phoenix A, with an event horizon spanning 370 billion miles, the distance from the boundary to the center is so vast that the change in gravitational pull across the length of a human body, roughly 6 feet, is negligible. The gravity is immense. The gradient, at that specific location, is not. So consider what this actually means in practice. An astronaut falling toward Phoenix A not accelerating, just drifting, following the natural curve of space-time, crosses the event horizon without any physical sensation marking the transition. No alarm sounds, no instrument reading spikes, no light show, no gravitational shudder, no moment of recognizable crisis. The space immediately surrounding them looks, by every local measurement, identical to the space they occupied a moment before crossing. Stars visible in the direction they came from, darkness ahead, the quiet of deep space in every direction, except every exit has just closed permanently. Every path through space-time that previously led outward, back toward the cluster, back toward the observable universe, back toward anything now curves inevitably inward, not as a force pulling them toward the center, but as a geometric fact. The structure of space-time inside the event horizon is such that moving forward in time is the same as moving toward the singularity. There is no direction that leads out. There is no thrust powerful enough, no trajectory clever enough, no physics available that permits a return. The boundary was crossed in a moment of complete normalcy, and the universe simply rearranged its geometry around that fact without announcing it. Death will come, but not yet. Hours, possibly days later, as the inward journey continues and the distance to the center decreases enough that the gradient finally steepens, the tidal forces will begin to assert themselves. Slowly at first, then with increasing insistence, then, at some point, much closer to the singularity, with a finality that requires no further description. But at the moment of crossing, at the exact location where the fundamental, irreversible transition occurred, there was nothing, no signal, no warning, a boundary invisible, unfelt, and absolute. Phoenix A is the most perfect trap the universe has ever constructed. Not designed, nothing designed it. But the combination of scale and physics produces an outcome that, if you were to engineer a trap from first principles, you could not improve upon. The entry is undetectable. The confinement is total. The exit does not exist. Now step outside. Imagine watching this from a ship hovering at a safe distance, instruments trained on the astronaut as they drift toward the horizon. You will never see them cross it. General relativity predicts, and observation confirms, that light emitted by an object falling toward an event horizon is increasingly redshifted and increasingly time-dilated as the object approaches. From the perspective of a distant observer, the infalling astronaut appears to slow down asymptotically. Their image reddens, it dims. It never actually reaches the horizon from the outside observer's point of view. The photons carry less and less energy. The gaps between them grow longer and longer, and the image fades toward invisibility over an arbitrarily long time. The astronaut appears to freeze at the boundary, suspended there forever, growing dimmer until they are effectively gone. Two observers, one event, two completely different physical realities, both of them correct according to the same underlying theory. The astronaut crosses the horizon, continues inward, experiences the interior of Phoenix A. The distant observer watches them freeze at the boundary and never arrive. Neither account is wrong. Neither is an illusion or an approximation. General relativity produces genuinely incompatible descriptions of the same physical event depending on the reference frame, and both descriptions are valid within that framework. Phoenix A, with its event horizon the size of a stellar system, is the largest natural laboratory in the observable universe. For this paradox, a place where the most profound conceptual tension in modern physics plays out at scales that dwarf everything else we have ever studied. A boundary you cannot see, a crossing you cannot feel, a death deferred until the geometry of space-time decides the time has come, a trap with a lobby that looks completely ordinary. The universe designed Phoenix A like the Hotel California of gravitational physics. You can check in at any time, drifting gently through an unremarkable-looking region of space, but you can never, under any circumstances, check out. And the worst part? The part that should keep you awake? Is that the lobby looks completely normal. Something this large, operating right now, had to come from somewhere, and when astronomers tried to trace it back to its origin, they hit a wall. The universe is not old enough for Phoenix A to exist by any method we understand. Supermassive black holes grow by eating. That is the standard model. And it is not a simplification. It is genuinely how the process works. Gas falls inward, heats up as it compresses, forms an accretion disk spiraling toward the event horizon, and a fraction of that infalling mass converts to energy, while the rest crosses the boundary and adds to the black hole's total mass. Stars get torn apart and consumed. Smaller black holes merge and combine over billions of years through countless cycles of feeding and dormancy. A black hole accumulates mass the way a savings account accumulates interest, slowly, consistently, with time doing most of the heavy lifting. The universe is 13.8 billion years old. That is a long time by any standard a human mind can access. Long enough, you would reasonably assume, for even the most extreme accumulation to reach genuinely enormous scales. 13.8 billion years of eating, merging, growing. Surely that is enough runway to produce anything we might observe today. It is not for Phoenix A, not even close. The critical constraint is something called the Eddington limit, a physical ceiling on how fast a black hole can consume matter. When material falls toward a black hole, it heats up and radiates energy outward. That outward radiation exerts pressure on the infalling gas. At a certain accretion rate, the outward radiation pressure exactly balances the inward gravitational pull, and if the black hole tries to eat faster than this equilibrium rate, the radiation simply blows the incoming material away before it can be consumed. The Eddington limit is not a rule someone invented. It emerges directly from the equations governing radiation pressure and gravity, and it applies universally to every accreting object in the universe. Now run the numbers on Phoenix A. Start with a seed black hole at the Big Bang generously, a seed of perhaps 100 solar masses, which is already on the large end of what stellar processes can produce. Apply the Eddington limit as the maximum growth rate, sustained continuously from the Big Bang to the present day, with no interruptions, no dormant periods, no inefficiencies of any kind. A completely unrealistic best-case scenario that treats the universe as a perfectly optimized black hole growth machine for its entire 13.8 billion year history. The result falls short of 100 billion solar masses. The math does not work. The universe has not had enough time to build Phoenix A through any standard accretion process, even under conditions far more favorable than anything we actually observe. This is not a matter of missing some detail in the calculation. This is a result derived from fundamental physical equations, the same equations that correctly describe the behavior of every other accreting system we have ever studied. Phoenix A does not sit at the edge of what the standard model predicts. It sits so far outside the standard model's predictions that the gap can't be bridged by adjusting parameters. Something is wrong, or something is missing, or both. The analogy is precise and genuinely unsettling. Imagine walking into a forest that was planted 100 years ago. Every tree you pass is between 15 and 20 meters tall, consistent with a century of growth, exactly what the biology of these species predicts. Then you step into a clearing and find a single tree 500 meters high, not slightly taller than the others, not an outlier at the edge of the distribution. 500 meters, an order of magnitude beyond anything the biology of tree growth, given the time available, can account for. You would not conclude that trees sometimes grow faster than expected. you would conclude that something fundamentally different happened to that tree. Something outside the framework you were using to understand the forest. Phoenix A is that tree, and the forest is the entire observable universe. What makes this genuinely alarming, not just scientifically interesting, but structurally alarming in the way that precedes major revisions to foundational theory, is that Phoenix A is not an isolated anomaly. It is the most extreme example of a pattern that has been accumulating force for years and reached a new level of urgency with the data coming from the James Webb Space Telescope in 2023 and 2024. JWST has been systematically finding massive black holes at redshifts that correspond to just a few 100 million years after the Big Bang. Objects that, by the standard model of black hole growth, simply should not be that large that early. Not slightly too large, dramatically too large, by factors that cannot be explained by invoking favorable conditions or above average growth rates. The problem is not limited to Phoenix A at cosmic noon. It appears throughout the history of the universe at multiple epochs, across independent observational programs using different instruments and different detection methods. Every new data release from JWST adds to the same growing body of evidence, pointing at the same uncomfortable conclusion. Some cosmologists have started using the phrase impossible early universe problem, the accumulating tension between what we observe and what our best models predict for the growth of massive structures in the early cosmos. It is not a term adopted casually. Physicists are conservative with language like that. When they start saying impossible, they mean we have checked the math, we have checked the observations, we have looked for systematic errors, and the discrepancy remains. Something in the foundational picture is either wrong or incomplete. The foundation of a theoretical building does not crack quietly. It cracks in ways that propagate upward through every floor built on top of it, through models of galaxy formation, through cosmological simulations, through our understanding of how the large-scale structure of the universe assembled itself over time. When the foundation shifts, nobody knows in advance which floor will show the damage first. If the universe did not have enough time to build Phoenix A, and the physics says clearly that it did not, then Phoenix A came from somewhere that the standard model does not describe? And if the answer to that question requires rewriting the cosmology of the early universe, the question that follows is not scientific. It is almost philosophical. Are we willing to follow the evidence wherever it leads? Even if it leads somewhere that dismantles frameworks that took generations to build. The universe, it turns out, did not consult those frameworks before deciding what to create. It built Phoenix A anyway, using what amounts to a cheat code that the designers of the game did not know existed. The rules said it could not happen. The object exists regardless, and the rules, accordingly, are going to need revision. So what is science doing with this mystery? They are building hypotheses, and some of them are strange enough to make you wonder whether we ever truly understood the early universe at all. The standard picture of supermassive black hole formation is orderly, incremental, and satisfying in the way that processes with clear mechanisms tend to be. It begins with stellar black holes, objects formed when massive stars exhaust their fuel and collapse, producing remnants of perhaps 10 to 100 solar masses. These seeds then grow through accretion. Gas falls in, mass accumulates, the black hole gets heavier. Along the way, mergers occur. Two black holes orbiting each other, radiating gravitational waves, spiraling inward until they combine into one larger object. Repeat this process across billions of years, across countless merger events and accretion episodes, and eventually you arrive at the supermassive black holes we observe at the centers of modern galaxies. Clean, logical, supported by a substantial body of observational and theoretical evidence for black holes up to a few billion solar masses. The process is slow, but the universe is old, and slow processes operating over vast timescales can produce impressive results. This is the framework every cosmology textbook was built on. And for most of the objects we study, it works. Phoenix A broke it completely. And now the field is working backward from the object to find a mechanism capable of producing it, which is a fundamentally different kind of science, less like building a structure and more like archaeology, sifting through the early universe for evidence of a process that left Phoenix A behind as its only known artifact. The first serious alternative is called direct collapse black holes, or DCBHS. The idea begins with a specific set of conditions that existed in the very early universe conditions that no longer exist today, and that may have been rare even then. In the first billion years after the Big Bang, enormous clouds of primordial gas, composed almost entirely of hydrogen and helium, were collapsing under gravity throughout the cosmos. In the standard picture, these clouds cool, fragment into smaller clumps, and form stars which may then produce stellar mass black holes through the conventional route. But in certain regions, where the ambient radiation field was sufficiently intense specifically, regions bathed in ultraviolet radiation from nearby star-forming galaxies, the cooling pathway was blocked. Ultraviolet photons destroy molecular hydrogen, the H2 molecule that normally allows gas to cool efficiently. Without molecular hydrogen, the gas cannot cool enough to fragment. It cannot form stars. And a gas cloud that cannot fragment cannot cool, and continues to collapse under its own gravity has only one destination. It falls inward as a single, massive object and forms a black hole directly bypassing the stellar phase entirely. The seed produced by direct collapse is not 10 solar masses, not 100. The initial black hole formed through this channel could be anywhere from 10,000 to 1 million solar masses, born fully formed in a single catastrophic collapse event. Start with that seed, place it in a gas-rich environment at cosmic dawn, and the arithmetic of reaching 100 billion solar masses over cosmic time becomes not easy, but at least plausible in a way that the stellar seed pathway simply is not. The second hypothesis operates at a different scale entirely. Hierarchical merging posits that Phoenix A is the product of repeated massive merger events, not of individual stellar black holes, but of already large black holes combining in the dense, chaotic environment of the early universe. In the first few billion years after the Big Bang, galaxy clusters were forming, colliding, and assembling through mergers at a rate that dwarfs what we observe in the modern universe. In this environment, protoclusters, the dense precursors to the massive clusters we see today, could have hosted dozens of large black holes whose host galaxies were continuously colliding and combining. The Phoenix cluster is, by observation, one of the densest and most massive galaxy clusters known. Its environment today is extreme. Its environment in the early universe before the mergers that built it had fully played out may have been even more so. A cluster this massive, assembled in an environment this dense, could have provided exactly the conditions for repeated hierarchical merging over billions of years, large black holes forming, sinking to the centers of their host galaxies, merging when those galaxies collide, producing progressively larger objects through a cascade of consolidations that standard accretion alone could never achieve. Both hypotheses require extreme conditions. Both push into regimes of early universe physics that we have, until recently, had almost no direct observational access to, and the truly unsettling possibility, the one that keeps theoretical astrophysicists running simulations at 3 in the morning, is that both may be simultaneously correct. Phoenix A may have begun as a direct collapse seed of hundreds of thousands of solar masses, formed in the first billion years of the universe's existence, and then grown through billions of years of hierarchical merging in the proto-Phoenix environment. The two mechanisms are not mutually exclusive. In the densest, most extreme corner of the early cosmos, they may have operated in combination. each amplifying the other's effect. The James Webb Space Telescope is beginning to provide the first real evidence. Among its deep field observations in 2023 and 2024, JWST identified several candidate objects displaying spectral signatures consistent with direct collapse black holes, sources in the early universe with properties that do not fit neatly into the stellar origin framework, but align with what DCBH formation would predict. These are candidates, not confirmations. The evidence is preliminary, contested in the way that all frontier observational claims are contested. But the candidates exist, and their existence shifts the DCBH hypothesis from speculative to plausible in ways that matter for how the field allocates attention and resources. If direct collapse is confirmed as a real formation channel, not just theoretically possible, but observationally verified, the consequences extend far beyond Phoenix A. The entire history of cosmic structure formation would require revision. Galaxy evolution models assume certain seed populations and certain growth timescales. Cosmological simulations are calibrated against observational data that, if DCBH formation was common in the early universe, may have been systematically misinterpreted. The large-scale structure of the universe, the web of filaments, voids, and clusters that we observe today assembled itself under rules that we thought we understood. If those rules included a formation channel we did not account for, every model built on that foundation is at least partially wrong. Phoenix A, in this light, is not merely a record-breaking object. It may be a living fossil, a surviving artifact of a process that operated in the first billion years of the universe's existence and has not operated at that scale since. Every other product of that process may have long since quieted, merged into larger structures, or become undetectable. Phoenix A endured, grew, and persisted into an epoch where we have instruments capable of finding it and asking what it is. You might be thinking this is a technical problem. Identify the right mechanism, plug it into the models, adjust the parameters, and the mystery resolves. That framing underestimates the scope of what Phoenix A represents. Finding the correct formation mechanism does not close the question, it opens the next layer of it. Because if a mechanism capable of producing Phoenix A existed in the early universe, the question immediately becomes, how common was it? How many objects did it produce? Where are they now? And what does their existence or the absence of their signatures tell us about the parts of the early universe we still cannot see? This is not a technical problem with a technical solution. It is a sign that a fundamental piece of the cosmic picture may be missing, not misplaced, not miscalibrated, but absent from the framework entirely. Astronomers approaching Phoenix A look like detectives working a case with crime scene evidence that is 5.7 billion years old, no witnesses, and a primary suspect that turns out to be the laws of physics themselves. The case is open. The evidence is extraordinary, and the detective work has barely begun. But while scientists argue over origins inside the Phoenix cluster, a catastrophe and a miracle are happening simultaneously, and those two things should not be able to coexist. In the largest structures in the universe, heat is a political problem. Galaxy clusters contain enormous reservoirs of hot gas. The intracluster medium sitting at temperatures of tens of millions of degrees, glowing brilliantly in X-ray light, filling the vast spaces between member galaxies like a sea of superheated plasma. This gas is always losing energy. It radiates, it cools, it gets denser, and eventually it begins to sink toward the gravitational center of the cluster under its own increasing weight, left unchecked. This cooling would drain the cluster's gas reservoir into the center over billions of years, triggering runaway star formation and fundamentally destabilizing the entire system. But it does not go unchecked. Not in most clusters, not most of the time. The central black hole acts as a regulator. As cooling gas falls inward and feeds the black hole responds, launching relativistic jets of plasma and energy outward along its rotational axis, driving powerful sound waves and shock fronts through the surrounding gas, depositing enormous quantities of energy into the intracluster medium and reheating it before the cooling can spiral out of control. The gas warms, its density drops, the infall slows, the feeding rate decreases, the jets quiet down, and the cycle resets. Astronomers call this AGN feedback, where AGN stands for active galactic nucleus. It is the universe's thermostat, a self-regulating feedback loop that has maintained approximate equilibrium in thousands of galaxy clusters across billions of years of cosmic history. It is one of the most important mechanisms in all of large-scale structure formation. Without it, the universe would look profoundly different from what we observe today. At the Phoenix cluster, the thermostat is broken, not slightly miscalibrated, not running a little warm. Broken in the way that produces consequences visible across 5.7 billion light-years of space and generates data so extreme that multiple independent observatories have flagged the system as categorically different from everything else in its class. Cold gas is pouring into the central region of the Phoenix cluster at a rate of approximately 2,000 solar masses per year. 2,000. In a typical massive cluster, the cooling flow, the rate at which gas sinks inward after losing enough heat, might deliver a few tens to perhaps 100 solar masses per year to the central region. Phoenix delivers 2,000 continuously, without the compensating heating that should, by every model we have, be keeping pace. The jets are there. Phoenix A is active, it is feeding, it is launching energy outward, but the jets are losing. The physics of why they are losing comes down to the specific conditions inside this cluster: an unusually high gas density combined with an unusually steep temperature gradient. The gas at the center of the Phoenix cluster is cooling so rapidly, radiating energy away so efficiently due to its extraordinary density that the energy input from AGN jets cannot reheat it fast enough to stop the infall. The feedback mechanism requires a certain amount of time to deposit its energy into the surrounding medium. The cooling in Phoenix does not give it that time. The analogy is exact. Imagine trying to heat a room in the middle of an Alaskan winter using a small desk fan fitted with a heating element. The fan is working. It is producing warm air. It is doing its job, but the room has a massive hole in one wall. The outside temperature is -40 degrees, and the rate at which heat is being lost through that gap simply exceeds what the fan can replace. Physics does not grade on effort. The room gets colder regardless of how faithfully the fan operates. The Phoenix cluster is that room, and the AGN jets of Phoenix A are that fan functional, but catastrophically outmatched by the conditions they were supposed to regulate. What we are observing is a cosmic scale control system failing in real time, not in a simulation, not predicted by a model, observed directly, measured precisely, confirmed by multiple independent instruments. The Chandra X-ray Observatory and the XMM Newton Space Telescope have both produced detailed temperature maps of the Phoenix cluster's intracluster medium, and both show the same result. The gas temperature at the cluster center is significantly lower than models predict for a system where AGN feedback is functioning effectively. The cooling is real, it is uncontrolled, and it is ongoing at a rate that has no parallel in the observational record. And when 2,000 solar masses of cold gas per year hit the central region of the cluster, the cascade that follows is not simple. Cold gas to gravitational collapse to star formation. New stars form and exert radiation pressure on surrounding gas, compressing nearby clouds and triggering further collapse. Supernovae from the most massive of these newborn stars inject energy locally, heating small pockets of gas, but at Phoenix. The overall cooling rate is so dominant that this local heating is absorbed without measurably slowing the system. The loop does not close. Each cycle adds more stars, more supernova, more energy input, but the underlying cooling flow continues undeterred, feeding the next cycle with the same relentless supply of cold infalling gas. Phoenix A itself sits inside this loop, not as the cause of the breakdown, but as one component of a system that is running well beyond its design parameters. The black hole feeds on infalling material, its activity level driven partly by the extraordinary supply that the uncontrolled cooling flow delivers. It launches jets. Those jets fail to halt the cooling. More gas falls in. The feeding intensifies. The loop continues. Phoenix A is not the villain of this story. It is the largest gear in a machine that has lost its governor, still turning, still functioning according to its own internal physics, but no longer part of a system that self-corrects. The question this raises is not comfortable to sit with. If the AGN feedback mechanism, the self-regulating system that maintains equilibrium in galaxy clusters across the observable universe, can fail under the right conditions, then the Phoenix cluster is proof that those conditions can be realized in nature. It is not a contrived scenario. It is not a theoretical edge case. It exists. It is operating right now, and we are measuring it. Which means the natural question is not just what happened here. The question is how many other clusters are approaching similar conditions. How many cosmic thermostats are running hot, losing ground incrementally, moving toward a tipping point we cannot currently detect. The Phoenix cluster is a warning embedded in data, and the data does not tell us it is unique. It tells us it is the most extreme confirmed case of something that the universe is, at least in principle, capable of producing elsewhere. The universe spent billions of years building a regulatory mechanism so reliable that it shaped the structure of the entire observable cosmos. Then the Phoenix cluster demonstrated that the mechanism has failure conditions, not theoretical ones, real ones, running right now at a scale that dwarfs every disaster our species has ever imagined. If that sounds familiar, a complex system with a seemingly reliable feedback loop that eventually encounters conditions outside its design envelope and fails catastrophically, it probably should. The consequence of a broken thermostat is not just cold gas falling inward. It triggers what astronomers call a cosmic scale starburst, and the number behind it will make you reassemble every concept you have about creation. The Milky Way makes stars at a rate of roughly 1 to 2 solar masses per year. This is not a limitation. It is a mature galaxy operating in equilibrium. Its gas supply, stellar feedback, and gravitational dynamics balanced into a steady, sustainable rhythm. 1 to 2 solar masses per year. Year after year. For billions of years. The stars that result from this measured pace have time to form planetary systems, to stabilize, to potentially host the conditions for chemistry complex, enough to eventually produce something capable of looking up and asking questions. Our sun is a product of that pace. So are we. Starburst galaxies operate differently. Objects like M82, the Cigar Galaxy, a classic starburst system sitting about 12 million light-years away, produce somewhere between 10 and 50 solar masses of new stars per year, driven by the gravitational disturbance of a close interaction with its neighbor, M81. By normal galaxy standards, this is extreme. By normal galaxy standards, a starburst galaxy is a factory running at emergency capacity, its gas reserves being consumed at rates that cannot be sustained indefinitely. Astronomers study starburst galaxies as exceptional objects. They appear in textbooks as examples of what happens when normal regulation breaks down. The central galaxy of the Phoenix cluster, is producing between 700 and 1,000 solar masses of new stars every single year. Not 10, not 50, between 700 and 1,000, 500 to 1,000 times the rate of the Milky Way, 20 to 100 times the rate of M82, which was already considered a system in crisis. The number sits there and resists comprehension in the way that only certain quantities cannot, because it is abstract, but because it is specific and measurable and confirmed by multiple independent observational programs, and it still does not feel like something the universe should be permitted to do. In the time it takes you to read this sentence, new stars are being born at the center of the Phoenix cluster. Not one, dozens each, potentially carrying more mass than our sun, each beginning a life cycle that will play out over the next few million years in an environment nothing like the quiet spiral arm where our solar system formed. While you read this paragraph, the number has increased further. The factory does not pause. It does not wait. It runs continuously, fed by the 2,000 solar masses per year of cold gas that the uncontrolled cooling flow delivers without interruption to the central region. Stop and sit with what 1,000 solar masses of star formation per year actually means. Our sun took approximately 50 million years from initial gas cloud collapse to stable main sequence star. 1,000 solar masses of material processed through that pathway every year, compressing, heating, igniting. Beginning fusion represents a creative output so vast that the word prolific cannot begin to carry it. And yet, this is not creation in any poetic sense. This is runaway industrial production, a factory operating 24 hours a day without maintenance, without quality control, without any mechanism to slow or stop output, and the product, rather than accumulating usefully, feeds back into a system already running beyond its limits. The stars being born in the Phoenix starburst are not quiet, long-lived objects like our sun. The gas supply favors the formation of massive stars, heavy, luminous, burning through their nuclear fuel at prodigious rates. A star 10 times the mass of the sun lives approximately 10 million years before exhausting its fuel and detonating as a supernova. A star 30 times the mass of our sun lives perhaps a few million years. These are geological timescales by human reckoning, but by astronomical standards, they are brief flash lives, bright and violent and short. The Phoenix starburst is producing enormous numbers of these objects, and they are burning through their existence at a pace that matches the frantic energy of the environment that created them. When they die, they do not go quietly. Supernovae, the explosive deaths of massive stars, are among the most energetic events in the universe. Each one releases more energy in a few seconds than our sun will emit across its entire 10 billion year lifetime. 1,000 solar masses of star formation per year, weighted toward massive stars, means a supernova rate at the center of the Phoenix cluster that dwarfs anything in our own galaxy by orders of magnitude. Each explosion injects energy into the surrounding gas, heats it locally, compresses neighboring clouds, and potentially triggers the collapse of additional star-forming regions. This is feedback loop number 2. Supernova generating energy that feeds further star formation, which generates more supernova, which generates more energy. In a normal galaxy, supernova feedback is a regulatory mechanism. It is part of what keeps star formation from running away. At Phoenix, the cooling rate is so dominant, the gas supply so overwhelming, that supernova feedback cannot keep pace. The energy is real, the heating is real, but it is absorbed into the larger system without altering the outcome. The loop continues regardless. The Hubble Space Telescope and the Chandra X-ray Observatory have both contributed to mapping what this system actually looks like in practice. Among the most striking findings, the existence of cold gas filaments extending tens of thousands of light years outward From the central region of the cluster, elongated structures of dense, cool material stretching through the hot intracluster medium like rivers of supply flowing toward a center that never stops consuming. These filaments are the delivery infrastructure of the starburst. They are the supply lines channels along which the cooling flow funnels cold gas from large distances into the central engine, ensuring that the factory never runs short of raw material, regardless of how rapidly it processes what it receives. 1,000 solar masses of stars created every year, and each of those stars might host planets, might generate the conditions for chemistry, might, in a different context, be the kind of stable system that over billions of years produces the conditions for complexity, for biology, for the kind of awareness that eventually wonders about its own origins, but not at Phoenix. These worlds, if they form at all, exist in an environment of relentless radiation, constant supernova, and gravitational chaos that makes the sustained stability required for life as we understand it essentially impossible. 1,000 potential solar systems born every year, and none of them given the time or the quiet to become anything more than fuel for a machine that does not know it is running. The Milky Way forms 1 to 2 stars per year, a pace so measured that even the DMV would find it unhurried. Phoenix manages 1,000. The difference is not between fast and slow. It is the difference between a craftsman working with intention and a factory that has been left running unattended and is now on fire. But why did Phoenix A wake up at this particular moment? And why did the thermostat fail specifically here? The answer lies in something you would not expect: an absence. Most galaxy clusters live violent lives. Not violent in the way that word implies on human scales. No explosions visible to the naked eye. No sound. No chaos that registers against the silence of deep space, but violent in the way that matters at cosmic scales mergers. Collisions between clusters, between subclusters, between the enormous concentrations of gas and dark matter and galaxies that make up these systems. When two clusters collide, the event unfolds over hundreds of millions of years, a slow-motion catastrophe that sends shockwaves rippling through the intracluster medium, stirs the gas into turbulence, redistributes energy across volumes of space that dwarf anything in our local cosmic neighborhood. These mergers are disruptive. They are also, it turns out, necessary. The Phoenix cluster has not had one, not recently, not in any time frame that leaves a detectable signature in the data. Look at the X-ray maps. Look at the temperature profiles. Look at the distribution of gas across the cluster's volume. What you find is something almost anomalous among massive clusters of its size and age symmetry: regularity. A structure that sits quietly, evenly distributed around its center, without the elongated distortions, the offset density peaks, the sloshing cold fronts, or the merger-induced shock structures that characterize the majority of similarly massive systems. The Phoenix cluster, by the standards of its own category, looks almost peaceful, orderly. A well-behaved system minding its own business in a corner of the universe 5.7 billion light-years from here. That apparent peace is the source of everything that has gone wrong inside it. In clusters that experience major mergers, the collision does more than stir the gas. The shock waves and turbulence generated by the impact continuously mix the intracluster medium, disrupting the formation of the cold, dense concentrations that feed cooling flows. When a merger is underway, or when the aftereffects of a recent one are still propagating through the system, the gas cannot settle. It cannot cool efficiently in one place because it keeps getting nudged, heated, redistributed. The chaos functions as a natural thermostat supplement, not replacing the AGN feedback mechanism, but working alongside it to prevent the conditions for runaway cooling from ever fully developing. Turbulence, it turns out, is doing quiet regulatory work that nobody appreciated until they found a cluster where it was absent. Remove the mergers, remove the turbulence, leave the cluster sitting in undisturbed symmetry with its extraordinary gas density and its unusually steep temperature gradient, the rate at which temperature drops from the hot outer regions toward the cool center. What remains is a system with no external mechanism to interrupt the cooling process. A gas supply dense enough to radiate energy away with exceptional efficiency, and a temperature gradient steep enough that the gas at the center is always cooler, always denser, always more prone to sinking than anything surrounding it. The conditions for an uncontrolled cooling flow are not just present, they are locked in, reinforced by the very stability that makes the cluster look, from the outside, like a model of cosmic orderliness, too stable, too symmetric, too undisturbed. The exterior calm accumulated interior pressure until the interior could no longer hold it. The parallel is not comfortable, but it is exact. A society without adequate pressure release mechanisms does not stay peaceful indefinitely. The absence of small conflicts, small disruptions, small renegotiations of the internal distribution of stress does not produce lasting stability. It produces the conditions for a failure that, when it finally comes, arrives at a scale proportional to how long it was suppressed. The Phoenix cluster ran its feedback loop without merger-driven turbulence for long enough that when the cooling flow finally exceeded the thermostat's capacity, it did so by a factor of hundreds, not a gradual slide. A system that had been building toward a tipping point for an extraordinarily long time, crossing it all at once. Phoenix A woke up because the supply became irresistible. 2,000 solar masses of cold gas per year pouring into the central region, not because something external triggered it, but because nothing external interrupted it. The absence of disruption was the disruption. The most extreme active black hole in the modern universe turned back on, not because something extraordinary happened to it, but because nothing happened around it for long enough. Astronomers are using this inversion deliberately. The Phoenix cluster is now functioning as a controlled comparison case, a system where the feedback loop has clearly failed, whose properties can be measured precisely and compared against clusters where the loop continues to function. By understanding in detail why Phoenix lost control, the field is building a cleaner picture of what prevents other clusters from losing control. Which conditions are necessary for stability, which are merely common? Which factors, if removed, push a system across the threshold? Phoenix is the failure mode that illuminates the success conditions, and the answer is more contingent, more dependent on specific circumstances than the simplified models implied. The broader implication is worth sitting with. Feedback mechanisms in cosmology, the regulatory loops that govern black holes, galaxies, and clusters are not robust universal laws operating identically across all environments. They are sensitive, conditional processes whose outcomes depend on specific local conditions, gas density, temperature gradient, merger history, cluster mass. Change any of those variables enough, and the outcome changes. The universe built a thermostat that works almost everywhere. Phoenix A is the proof that almost everywhere is not the same as everywhere, and the difference between those two phrases is, apparently, an uncontrolled cooling flow feeding the most massive black hole ever found. You might think stability is good, in life, in institutions, in systems of all kinds. Stability is the goal. Phoenix A says otherwise. Sometimes perfect stability is just energy accumulation, waiting for a release that the system was never designed to absorb. The universe needed a little chaos to keep its balance, and the Phoenix cluster, too well behaved for too long, is the proof. The universe needs a little chaos to maintain balance. It turns out this principle applies equally to galaxy clusters and Thanksgiving family dinners. But this loss of control is not only a catastrophe. For scientists, it is something rarer and more valuable, a window. Phoenix A is showing them something the universe spent 10 billion years hiding, and no instrument humans have ever built could replicate what this single broken system is offering for free. Light from the sun takes 8 minutes to reach us. Light from the moon takes roughly 1.2 seconds. Light from Proxima Centauri, the nearest star beyond our own, takes 4.2 years. Every telescope ever built is, in a precise physical sense, a time machine pointed at something far enough away. And you are not seeing what is there now. You are seeing what was there when the light left. The universe does not transmit live. It transmits recordings, delayed by distance, delivered at the speed limit of physical reality. Most of the time, this fact sits in the background as an interesting footnote. The delay from the sun is 8 minutes, negligible for almost any practical purpose. Even Andromeda, the nearest large galaxy, delivers light 2.5 million years old. Significant by human measures, but in the context of cosmic history, not far back. We are still, in a sense, looking at the recent universe. Phoenix A is different in kind, not just in degree. 5.7 billion light-years away. That number means the light arriving at our instruments today left the Phoenix cluster 5.7 billion years ago, before our sun ignited, before the disk of gas and dust that would become our solar system had begun to coalesce, before Earth existed in any form. The Milky Way was there. But the particular arm of it, where our sun would eventually form, was still waiting for the stellar generations whose deaths would seed it with the heavy elements needed to build rocky planets. There was no solar system. There was no Earth. There was no you, no anyone who would eventually become you. No biological lineage that would eventually produce a species capable of building instruments to detect the light now completing its journey. We are not watching Phoenix A as it currently exists. We are watching it as it existed in a universe that our own solar system had not yet joined. That is what 5.7 billion light-years means in human terms. But the distance is not only a delay, it is a destination. Astronomers believe that the majority of large galaxies, including the Milky Way, assembled their bulk through processes that operated most intensely when the universe was young and dense and actively producing stars at rates that the modern cosmos does not approach. The early universe was different in character from the one we inhabit, hotter, denser, packed with gas that had not yet been consumed, dominated by the kind of intense activity that produces quasars, starbursts, and rapid black hole growth. The galaxies we see today as mature, stable, slowly evolving systems, our own among them, are the products of that early intensity. They carry the signatures of it in their stellar populations, their chemical abundances, their structural properties. But the process itself, the violent, rapid assembly phase, is over for them. What remains is the aftermath. Phoenix A is not the aftermath. Phoenix A is the process, still running, directly observable, measurable with current instruments in real time. The starburst producing between 700 and 1,000 solar masses of new stars per year, that is not a fossil of early galaxy formation. That is early galaxy formation, happening right now in our telescopes, at a distance that places it in the epoch when this kind of activity was supposed to be common. The cooling flow delivering 2,000 solar masses of cold gas per year to the central region, that is the raw material delivery system of a galaxy in its assembly phase. The AGN activity, the jet launching, the X-ray luminosity that breaks every cluster record. All of it is the physics of a galaxy being built, compressed into an object close enough in cosmic terms to study in detail. The Milky Way went through something like this. Every large galaxy did. But by the time we developed the instruments to study it, our own galaxy's violent youth was billions of years in the past, readable only in the chemical compositions of old stars. in the orbital properties of stellar populations that formed in different environments, in the subtle imprints left on structure by processes that finished operating long before complex life existed anywhere. Reading that history from fossils is extraordinary science, but it is archaeology. It is inference from evidence rather than observation of the event. Phoenix A is the living animal, not the fossil, not the bones in the ground, not the preserved footprint in ancient rock, the actual creature, moving, breathing in the cosmological sense, doing right now what our galaxy did billions of years before it could be observed. Finding it is the equivalent of paleontologists spending careers reconstructing dinosaur anatomy from fragments of fossilized bone, and then walking out of the lab one morning to find a living specimen grazing in the parking lot. The science that was being done carefully and indirectly can now be done directly. The process that was being inferred from its products can now be measured as it operates. The data from Phoenix A is already doing this work. Cosmological simulations, Illustris TNG, Eagle, and others represent the state of the art in modeling how galaxies form and evolve across cosmic time. These are not simple models. They run on some of the most powerful supercomputers available, incorporating gravity, gas dynamics, star formation, black hole physics, and feedback processes across volumes of simulated space spanning hundreds of millions of light years. They are calibrated against observational data accumulated over decades. They represent the best current synthesis of everything known about how the universe builds its large-scale structure. They cannot reproduce Phoenix A, not fully. The simulations produce systems with elevated star formation, with active black holes, with strong cooling flows, but not at the scales Phoenix delivers, not in the combination Phoenix delivers, not in a system with the specific properties Phoenix possesses. The discrepancies are not trivial rounding errors. They are systematic, and they point in a consistent direction. The models are missing something, or misrepresenting something, about the extreme end of the distribution. Phoenix A is ground truth, a direct observational measurement of what actually happens in the most extreme cluster environments, and it is revealing the boundaries of what current simulations can handle. Every time the simulations fail to reproduce Phoenix A, that failure is information. It locates, with increasing precision, where the model's assumptions break down. It identifies which physical processes are being oversimplified, which parameters are being set at values that work for typical systems, but fail at extremes, which interactions between gas dynamics, black hole feedback, and star formation are being captured inadequately. Phoenix A is not just a record-breaking object. It is a calibration instrument, the most extreme test case available for every theory of galaxy formation and cluster evolution that the field has built. The process that created our galaxy, that created the conditions for our sun, that ultimately created the conditions for you. We are watching a version of it right now at 5.7 billion light years, measured in X-rays and millimeter waves and optical light by instruments on orbit and at the South Pole. We do not fully understand what we are seeing. The simulations that should reproduce it fall short. The models that should explain it are being revised. And in that gap between what we observe and what we can explain sits the most important knowledge the field is currently trying to extract: the operating instructions for the process that built everything we know. Phoenix A is essentially the universe's origin story playing live. No subtitles, and astronomers are sitting in the audience with notepads and pencils, trying to follow the plot. But all of this, the scale, the mystery, the starburst, the time machine, is still just data until you ask the real question. What does any of it mean for us, the small creatures looking up at the sky, trying to put names on things incomparably larger than ourselves? We think we know the universe reasonably well. Not completely. Nobody claims that, but in broad strokes. In the way you might say you know a city you have lived in for years. You know the major landmarks. You know the categories of things that exist there. You know roughly how many of each kind there are, and where they tend to cluster, and what the overall shape of the place looks like from above. The universe, in this framing, is a known quantity at the level of its major features, hundreds of billions of galaxies, each containing hundreds of billions of stars, organized into filaments and voids and clusters across a volume 13.8 billion light-years in radius. We have the map. We understand the legend. We know what the symbols mean. Phoenix A should make you question every part of that confidence. Ultramassive black holes do not announce themselves. That is the first problem, and it is a serious one. An active system like Phoenix A, feeding at high rates, launching jets, driving a starburst, blazing in X-ray light across 5.7 billion light-years is detectable precisely because it is doing all of those things at once. Strip away the activity, allow the black hole to enter a dormant phase, as Phoenix A itself did for hundreds of millions of years before its current awakening. The jets stop, the accretion disk dims, the extreme X-ray luminosity fades. What remains is an object of 100 billion solar masses sitting at the center of a dense galaxy cluster, surrounded by gas that absorbs and scatters the faint signals still being emitted, effectively wrapped in a shroud of its own environment. From the outside, looking in with current instruments, a dormant ultramassive black hole in a dense cluster is close to invisible, not difficult to detect, not faint, but findable with enough exposure time. Close to invisible because the very environment that feeds these objects when they are active is the same environment that conceals them when they are not. The gas that drives the cooling flow, that delivers raw material to the accretion disk, that sustains the starburst, that gas, when the black hole is quiet, sits between us and the object like a wall of fog with no obvious opening. The confirmed and candidate ultramassive black holes currently known number roughly a dozen. A dozen, in an observable universe containing an estimated 2 trillion galaxies. That number is not a census. It is a lower bound and almost certainly a severe underestimate of the actual population. Conservative estimates from theorists suggest tens to hundreds of UMBHS may exist in the observable universe that current surveys have not detected. Some estimates go higher. The honest position is that nobody knows, because the tools required to find dormant objects of this kind in dense cluster environments are only now being developed to the sensitivity required. Sit with that for a moment. The most extreme objects in the known universe, entities with event horizons spanning hundreds of billions of miles, containing mass equivalent to 100 billion suns, may be sitting undetected in the dark, scattered across the observable universe. Waiting. Not metaphorically waiting. Physically dormant, as Phoenix A was dormant, as every black hole periodically becomes when its gas supply temporarily drops below the threshold needed to sustain visible activity. Dormant and invisible and present. Now layer that on top of what we already know about the inventory problem in cosmology. Roughly 27% of the universe's total mass energy content is dark matter detectable only through its gravitational effects. Never directly observed, its fundamental nature still unknown after decades of dedicated searches. Roughly 68% is dark energy the name physicists gave to whatever is driving the accelerating expansion of the universe, a label that describes the phenomenon without explaining it at all. That leaves approximately 5% of the universe's total content in ordinary matter, the protons, neutrons, and electrons that make up everything we have ever directly detected or touched or measured. Everything. Every star, every planet, every galaxy, every instrument we have ever built, every atom in every human body that has ever existed. 5%. We have built our entire understanding of the cosmos on 5% of its contents. and within that 5%. It now appears that the most massive objects may be systematically underrepresented in our catalogs because of a detection bias that preferentially finds the ones that happen to be active at the moment we look. The map we drew is not wrong, but it is a map of the room's furniture drawn by someone who has never turned on the lights and may have missed everything stored in the closets. The feeling this produces is not the clean collapse of knowledge. It is something subtler and in some ways more disquieting, the recognition that the iceberg below the surface is larger than previously assumed. The visible portion, the part sticking out of the water, the part we have cataloged and named and built theories around, is real. The science built on it is real, but its relationship to the total is different from what we thought. And the difference is not a small correction at the margins. It is a structural reassessment of how much of the picture we are actually seeing. The next decade will begin to answer some of these questions. The Vera Rubin Observatory, a large synoptic survey telescope in Chile designed to photograph the entire visible sky repeatedly, building up a time domain record of how the universe changes, will bring detection sensitivity for indirect UMBH signatures that no previous facility has matched. The Square Kilometre Array, a radio telescope network being built across South Africa and Australia with a combined collecting area of 1 square kilometre, will probe cluster environments at radio wavelengths with a resolution and sensitivity that may reveal dormant, ultramassive black holes through their subtle effects on surrounding gas. These instruments are not refinements of existing tools. They represent categorical improvements in our ability to see things we have been blind to, and what they find, when they come fully online, will almost certainly complicate the picture further rather than simplify it. Every new UMBH discovered adds a data point. Every data point changes the statistical picture and the direction in which the statistical picture has been moving consistently across every instrument upgrade and every new survey is toward a universe that contains more extreme objects than previous estimates predicted, distributed more widely, active across a longer span of cosmic time, and concealed more effectively by their environments than the simplified models assumed. The trend line does not suggest that the next generation of instruments will find a handful of new objects and close the inventory. It suggests that what we currently know about ultramassive black holes is the beginning of an answer, not the end of one. If hundreds of Phoenix A equivalents are dormant in the dark right now, what wakes them? The answer, as Phoenix itself demonstrated, is a breakdown in the systems that keep them quiet. A cooling flow that exceeds the thermostat's capacity. A merger that delivers a sudden surge of fresh gas. A cluster environment that, through some combination of density and temperature and history, crosses a threshold and tips from regulated to runaway. These conditions are not rare in principle. They are rare in the sense that the specific combination required is uncommon, but uncommon across 2 trillion galaxies still produces a substantial number of events. And when they wake, who sees? We thought we had drawn the map fairly well. It turns out that map was sketched in pencil on a small piece of paper of one room in a building that we have never seen from the outside. But what truly haunts is not the things we have not yet found. It is what happens when you place Phoenix A in its full temporal context. Because when you do that, when you stop measuring in light years and start measuring in the only currency that captures what Phoenix A actually represents, the position of humanity in this story changes completely. Human civilization measures itself in thousands of years. The oldest continuous civilizations, Egypt, Mesopotamia, China, stretch back perhaps 5,000 to 7,000 years. Rome rose and fell in roughly 1,000. The entire span of recorded human history, from the first written symbols pressed into clay tablets in ancient Sumer to this present moment, fits inside approximately 5,000 years. We treat this as a long time. In the context of human experience, it is. Earth is 4.6 billion years old. Life appeared on it approximately 3.8 billion years ago. Complex multicellular life is roughly 600 million years old. Homo sapiens, our species, the one building telescopes and writing papers and arguing about black hole classification, has existed for approximately 300,000 years. These are large numbers by human standards. They are also, in the context of what we are about to discuss, not very large at all. Phoenix A has existed for at least several billion years. It has cycled through periods of furious activity and long dormancy, feeding and quieting and feeding again, across timescales that make the entire history of life on Earth look like a single page in a very long book. The most recent dormant phase, the hundreds of millions of years of near silence before the current awakening, lasted longer than the entire span from the Cambrian explosion to the present day. Everything that happened in that span, the Cambrian itself, the colonization of land, the rise and extinction of the dinosaurs, the diversification of mammals, the emergence of primates, the evolutionary lineage that eventually produced us, all of it occurred within a single rest period of Phoenix A, not its entire history, one nap. 500 million years of dormancy. In that same 500 million years on Earth, 5 major mass extinctions reshaped the biosphere. The Ordovician extinction wiped out roughly 85% of all species. The Permian extinction, the largest in Earth's history, eliminated an estimated 90 to 96% of all marine species and 70% of terrestrial vertebrate species. The Cretaceous extinction ended the reign of non-avian dinosaurs entirely. Between these catastrophes, entirely new body plans evolved, entire ecosystems assembled and collapsed and reassembled, and a lineage of small furry mammals survived, diversified, developed grasping hands and forward-facing eyes, came down from the trees, stood upright, developed language, and eventually began asking questions about the universe. All of that, every bit of it, inside one dormant phase of Phoenix A. Now compress further. Take the 5,000 years of recorded human history, the pyramids, the Roman Empire, the Renaissance, the Industrial Revolution, the 20th century with its wars and its physics and its space programs, the internet, everything, and place it against 500 million years. The ratio is 1 to 100,000. Every dynasty, every empire, every scientific revolution, every technological leap our species has made the entire written record of human thought and achievement occupies 100,000th of the duration of Phoenix A's most recent period of rest. Not its active phase, its rest. This is not an argument for human insignificance. That framing misses the point entirely, and the point is worth getting right. The Egyptian pyramids were built by people who had no concept of galaxies. The Roman engineers who constructed aqueducts did not know that the sun was a star. The scientists who developed quantum mechanics in the early 20th century were working without any confirmed image of a black hole. In 300,000 years, a cosmological eye blink, our species went from stone tools to radio telescopes, from campfires to instruments capable of detecting light that left its source before our solar system existed. That trajectory is not diminished by Phoenix A's scale. If anything, it makes the trajectory more remarkable. But the scale resets the proportions. It insists on accuracy about what we are and how long we have been here relative to what we are studying. Phoenix A will still be there when our sun dies. The sun has approximately 5 billion years of hydrogen fuel remaining. When it exhausts that fuel, it will expand into a red giant, likely engulfing Mercury, Venus, and possibly Earth, before shedding its outer layers and contracting into a white dwarf, a dense, slowly cooling remnant roughly the size of Earth, but containing roughly half the sun's current mass. That process will take billions of years to complete. Phoenix A will watch it, in the sense that it will exist throughout it, cycling through its own phases of activity and dormancy, consuming gas and launching jets and building mass, indifferent to the fate of a small star in a spiral galaxy 5.7 billion light-years away. After the Sun becomes a white dwarf after Earth, if it survives, has been sterilized by the red giant phase after whatever remains of our solar system has cooled into the dark phoenix. A continues. It doesn't wind down on any timescale that connects to ours. It does not notice. It does not require witnesses. It exists on its own terms in its own time, governed by physics that operates at scales we can measure but cannot fully inhabit imaginatively. And yet, this is the thing worth holding on to. We are here, right now, in this specific cosmological moment, on this specific planet, with this specific combination of intelligence and curiosity and instrument building capability. We found it. We pointed telescopes at the right patch of sky, built detectors sensitive enough to capture its signal across 5.7 billion light-years, ran the numbers, checked them, published the results, and understood at least partially what we were looking at. Phoenix A's existence does not require us, but our awareness of it is, by any reasonable measure, one of the stranger things the universe has managed to produce. You reading this right now exist in an astronomically brief window. Before you, by cosmic standards, essentially nothing recognizable as awareness existed here. After you, by the same standards, Phoenix A will cycle through phases of activity and dormancy for longer than the current age of the universe. You are located, in time, at a vanishingly thin slice between two vast darknesses, and in that slice, you are somehow aware of both of them. Phoenix A existed before Earth formed and will continue long after Earth is gone. Our entire history, every word ever written and every thought ever recorded, is a parenthesis in its biography, a very small one. And this is the final thing, the thing that, when you actually sit with it, will not leave your head for days. What does it mean to know any of this? Science gets told as a conquest story. That is the default narrative, the one that shows up in textbooks and documentaries, and the way discoveries get announced to the public. We did not know, now we do. The universe was dark, now there is light. The mystery existed, now it is solved. Each chapter ends with an answer, and the answer closes something. And the closing feels like progress, because it is progress. And progress feels good because it should. That narrative is not false. It has carried our species from candles to particle accelerators, from superstition to general relativity, from not knowing the Earth orbits the Sun to putting instruments in orbit around other planets. The conquest story earned its place. Phoenix A does not end with an answer. Its origin unresolved. The formation mechanism that produced 100 billion solar masses in a universe not old enough to build it through standard processes. Still open, still contested, still generating competing hypotheses that the data has not yet decisively separated. Its full internal physics, beyond the reach of any model currently trusted to give reliable results at that mass scale. Its future unpredictable in the specific sense that the system driving it, the uncontrolled cooling flow, the starburst, the feedback loop running without a governor, has no clear endpoint that current theory can calculate with confidence. And every partial answer the field has managed to extract from the data has opened, reliably, more questions than it closed. The redshift measurement that confirmed its distance revealed the timeline paradox. The X-ray luminosity that established its cluster records revealed the thermostat failure. The starburst rate that broke every benchmark revealed the absence of any mechanism capable of stopping it. Each answer was a door, and every door opened onto a longer corridor. This is not a failure. It needs to be said plainly, because the temptation to read it as failure is real. This is not science running out of explanations. This is science operating exactly as it operates when it encounters something genuinely large. Something that does not fit the categories built to contain it. Something that arrives at the edge of the map and keeps going. The best current frameworks all find their limits at Phoenix A, Lambda C D M cosmology, the standard model of cosmology, the framework that successfully describes the large-scale structure of the universe, the cosmic microwave background, the distribution of galaxies across billions of light years, cannot straightforwardly account for Phoenix A's mass given the time available. General relativity, the most precisely tested theory in the history of physics, describes the geometry of space-time around Phoenix A's event horizon, but cannot tell us what the interior looks like at 100 billion solar masses in any way that has been observationally verified. The AGN feedback models that correctly describe thousands of other clusters fail to reproduce what is happening inside the Phoenix cluster at the rates being measured. The frameworks are not wrong. They are meeting their boundaries, and their boundaries are exactly where Phoenix A sits. Standing at the edge of what is known and looking into what is not, that is not a failure condition. That is the most advanced position a species can occupy in its attempt to understand the cosmos. Every major expansion of human knowledge began exactly there at the place where the existing framework produced results that did not match what was being observed, where the map ran out and the territory continued, where the honest answer was not, "we know," but "we know that we do not know, and we know approximately where the gap is." That second kind of knowing precise ignorance, located ignorance, ignorance that points in a specific direction, is the precondition for every discovery that followed it. Now the layer that changes the meaning of everything above it. Every species that has ever existed on Earth and the fossil record suggests there have been somewhere between 1 billion and 4 billion species over the past 500 million years. Exactly one developed the cognitive architecture to look up at the night sky, recognize that the points of light are objects, build instruments to measure their properties across billions of light years, and arrive at a precise, quantitative understanding of something like Phoenix A. One, not most, not many, one species, on one planet, orbiting one unremarkable star in one of hundreds of billions of galaxies, in a universe that has been running for 13.8 billion years without requiring any of this to happen. That does not make us greater than Phoenix A. The comparison is not meaningful. Phoenix A is a gravitational system operating on scales that have no relationship to biological significance, but it makes the capacity for awareness the specific, improbable ability to look outward and understand one of the strangest phenomena the universe has produced in its entire history. The universe built Phoenix A through gravity and gas and time. It built us through an entirely different process, operating on entirely different scales. And the product of that process is something that can detect, measure, and partially comprehend the first thing. Through us, the universe is doing something it did not obviously need to do, looking at itself. If Phoenix A existed for billions of years without any awareness in the universe registering its presence, and it did for most of its history, then what does our awareness of it add not to Phoenix A? Nothing is added to Phoenix A by being observed, but something is added to the universe's own account of itself. A fact that existed without a witness gains a witness. A process that operated without being understood gains partial understanding. That may seem like a small thing against the backdrop of 100 billion solar masses and 370 billion miles of event horizon. It is a small thing, but it is also the only kind of thing that asks whether it is small. If Phoenix A has existed for billions of years without anyone knowing, then what does it mean that we know? And if there are things out there still larger, still stranger, still sleeping in the dark? Should we look for them, even knowing the answers might break everything we currently believe? We creatures living 80 years on a small planet around an ordinary star in an ordinary galaxy found Phoenix A, named it, measured it, and are now losing sleep over its philosophical implications. The universe almost certainly did not see that coming. And perhaps that is the most astonishing thing in this entire story. 100 billion solar masses, 370 billion miles of event horizon, 1,000 new stars every year, burning fast and dying faster, feeding a loop that nothing in the cluster can stop. Step back from all of it, from every number, every record, every broken model, and what remains is not a data set. Phoenix A is a living question about what the universe is and what it permits and how much of it we are actually seeing. Its origin unsolved, its future open. The physics of its interior beyond the reliable reach of every framework we trust, that is not a conclusion. It is an invitation. Standing at the edge of understanding and looking into what lies beyond it, that is where every genuine discovery has always started. Phoenix A will keep cycling long after our sun is gone, long after anything we have built has ceased to exist, through generations of humanity not yet born, and perhaps through the absence of humanity entirely. It does not need us. It never did. But we are here, right now, looking. No answers. Just the night sky, and out there, 5.7 billion light years away, something waking up and feeding, with no knowledge and no need to know that anyone is watching.